right, we'll get started. We have a very exciting event, one of my favorites. Actually, earlier in the year, I predicted that the biggest focus will be multimodal, going beyond just the language models, which look at the text data. And I think there was some early uh, evidence that as the year ends, we are likely to get into more multimodal. And today we have two very, very exciting speakers, and we have some really amazing work that they have done to share. Uh, but for a lot of you who are joining us for the first time, thank you and welcome for joining. We are in our December 2024 BrainX Community Live event. Over here, we'll be recording this. For those of you who are joining us for the first time, we started this platform 6+ years ago to be able to have one unified platform for machine learning in healthcare for good, and so that we can provide all the resources and content to everyone for free. And that's been our endeavor. Now we've grown to be 6,000 plus member international community and growing. We have a very active LinkedIn group, which is very focused on sharing scientific information, opportunities to share your scientific information on your great work. We, of course, have a repository of content called our website, brainxai.org, and I'll show you snippets of that. And then we do these monthly sessions where we can interact with some of the amazing speakers, researchers, developers, innovators who are for AI in healthcare. So this is our homepage, and if you go over there, you will find the latest and the greatest news right there. And it has links to various different subsections. So Connect is our very popular section where we put information about our future monthly events. And also, once they have finished, we have the recording link right through that available to you. And the recording goes on our popular YouTube channel. So if you haven't subscribed it yet, please subscribe it so that you, as soon as we have the recording available, it will come to your inbox and you can watch it even if you miss it. As I mentioned, we have a very active LinkedIn group sharing a lot of scientific information. So if you haven't joined yet, I would encourage you to look at it and join BrainX Community LinkedIn group. We have a Learn section where we provide a whole host of publications. Now, the number of publications has just exploded over the last so many years. So we curate it for you. We provide the filtering based on the healthcare specialty that you might be interested in and be focused on. And of course, we can provide all the publications. I wish they were all open source, but we provide direct links so that you can directly go to those publications. They are categorized and you can filter them. And one of our most popular sections is the data section. Everybody is looking for data to develop their models. And there are a lot of open source data sets which are available for research and require minimal DUA agreements. So you can go to our data section. You can look for the different data sets. You can again filter them for different healthcare specialties. And even the data set for the echocardiograms that our researchers have worked on is available is linked over there. And of course, the data sets for large language models or foundation models have also been growing. So if you're interested in looking at those, you can filter the data section for that and get some of those data sets and get your work going. We have our podcast series where we interview and have some of the eminent scientists featured. We try to get their stories. They might be clinicians, they might be machine learning experts, they might be innovators, but you want to listen to their story. You want to learn from them. You want to understand their vision for the future. So that's why we feature them over there. And hopefully you can learn from their experience and grow the same way for AI in healthcare. And of course, we want to meet you. We want to connect with each other. We want to showcase our work. So we provide a curated list of meetings or conferences that are coming up so that you can participate there. You can learn. You can showcase your amazing stuff, your research work over there. So we provide this curated list through the meeting section. We also provide a whole host of frameworks and tools. This is from BrainX, which is Humanely, which is a human evaluation tool. We provide it for free so that people can perform human evaluation of the large language models, the only tool that is available out there for any kind of LLM output human evaluation. And we just put out a book earlier in the year, along with Frank Pepe and Jeffrey Magnus, The Strategies for AI in Healthcare, which talks about how you can go about building a team, what you need, and how you can achieve success for AI in healthcare projects that you might be looking for. But more important, I'm really, really excited about this. That's why I think I saved the best for the last, which is Echoprime. It is about automating echocardiography information with artificial intelligence, amazing foundational model development work. And one way I think about this is also the democratizing of skill sets and knowledge using AI. It is very hard to have these skills. So people have to train for a long time. There are certification courses. There are all these years of experience that is required. But then you think about the patients who need this information and the clinicians who need this information. And can AI help deliver that in a in a reasonable way, in a good way, so that we can democratize access to this important technology to everyone. And I see this as a great work that precedes how this automation can go and help our patients. So it's a very practical, very useful tool. I love the multimodal aspects of that. I invite our eminent speakers. If I mispronounce their names, I apologize in advance. We have Milos, who's a PhD candidate at UCLA and a visiting graduate student at Cedars-Sinai Medical Center. Amazing work that he has done leading this foundation model, working with Dr. David Hoyang, who we had featured previously. And we have Hai-Men Chiu, who is an ER physician. He has a PhD in computer science and an AI research scientist at Cedars-Sinai too. And just recently, more than Echoprime, I also saw their amazing work related to the pericardium or the pericardial disease diagnosis. So I hope they can share some of that work too through this. So I will hand it over to both of them for rest of the presentation. We will be happy to take questions and any of the comments. Please put them in chat. But I welcome Milos and Dr. Chiu to proceed with their presentation.
All right, thank you, Piyush. So we structured the presentation in the following way. I'm going to talk first. I'm going to show a few slides first, and then we can move on to the live demo of our model. And as like concluding remarks, Emin can share what are the implications and future directions for such research in clinical setting. So you can see my screen, right? Okay. Right, so our presentation is AI for comprehensive cardiac ultrasound exam interpretation, and it is, let me just move this. And it is the research that we did as a project, in a project that we recently published a preprint on called Echoprime, multi-video view informed vision language model for comprehensive echocardiography interpretation. I am a PhD candidate at UCLA, and I'm also a visiting graduate student at Cedars-Sinai. Emin is my colleague at Cedars-Sinai, so we work in the same lab under Dr. David Oyang. All right, so I know that this is a clinical audience, but I'm just going to reiterate over the standard echocardiography exam workflow so that we can see where does AI come in here. So echocardiography is the ultrasound procedure. It uses sound waves to create images of heart and the nearby blood vessels, and it's the most widely used imaging modality. If we see the graphics on the bottom, so you can see the standard pipeline of an echocardiography exam. So first, a sonographer captures multiple 2D videos of the heart, slicing it from different angles to visualize various structures. And then these videos are being sent. So all the many videos are obtained for one single patient, and then all these videos are being sent to a cardiologist who inspects them and writes the interpretation report. And also, by the way, I see that there is already something in the chat, but feel free to ask anything, any questions, or interrupt me during the presentation, or save your question for the end. I'm good either way. Okay, so So given this, knowing the echocardiography exam pipeline, AI could automate different, it showed promise in automating different parts of this pipeline. For example, it has been used in tasks like regression, for example, predicting measurements such as ejection fraction. It has been used in segmentation, such as segmenting the different tissues, or in this specific case, in the top right, the LV, left ventricular mass. It has also been used in classification, such as assessing the severity of diseases, for example, mitral regurgitation. And interestingly, recently it has been used to generate new images from scratch, either for purposes of making big data sets or just modifying the image so that it can be analyzed or simulated pre-surgery. But we think that all these current models are somewhat limited, mostly because they focus on a single frame, a single video, and are trained only to predict a single task. So you can imagine that given all these videos that are obtained during one echocardiography exam, most of the current models just pick a single video and then cut out a single frame from this video, and that's their input. And then they predict only a single feature, such as in this case, I gave an example of mitral regurgitation is present or not. And you can see how limited this is and how much information is being left out. And that is why our goal here in the project is to make an AI that works like a cardiologist. So we want a model that can synthesize the information across all echocardiography views and write a report describing each anatomical section in detail. So we believe that that's how cardiologists do it, and we want an AI that does it in a similar way to cardiologists. And right now, in comparison between previous models and our model, we, as you can see, we aim to take the information from all the videos, right? And then process the temporal data, not only the single frame from the video. And then given that, predict section by section, analyzing it in detail instead of just a single disease or a single feature. All right, so that was the goal once we started this project, and now I'm going to talk about how we successfully achieved it. The first part of every machine learning pipeline is collecting the data set and processing it. We work at Cedars-Sinai, so we were able to get a big retrospective data set collected, I think, from 2000 to 2022, including 108,000 patients, 12 million different echocardiography videos, 280,000 studies, and 68 million report words. These are some of the features of the data set. This is the data set used for training the model, and then we collected a few external data sets. Specifically, the reports that are written, so echocardiography reports, you can see the histogram on the bottom left, and on average it has like 250 words, whereas for the videos we measure the length in frames, and histogram shows that on average there are like maybe 60 frames per each video. And then for the report sections, the bar plot on the right shows us that left ventricle is the most verbose section, then aortic valve, then IVC, meaning probably that these are most informative about the cardiac health. But right, it just shows also how many, what is the bulk of the data needed to train such a model. And for the external data sets, in the preprint that we already published, we already evaluated Echoprime on Stanford healthcare dataset that includes 1,800 patients from 1,800 studies from 1,800 patients, and that's about 90,000 videos. We also are in the process of evaluating it on mimic dataset. So this is, I think, from Beth Israel Medical Center. We were able to process 2,500 studies and their corresponding reports. And then with Imin's help, we were able to get the data from CGMH hospital in Taiwan that I think currently we have 1,200 processed studies. So let me see if there are any questions. Okay.
Milos, we'll take the questions at the end. I'm just adding some information in the chat in the meantime.
All right. Yeah, thank you. Okay, so I was describing the data that we have, and now we can move on to the model design. I'll spend some time on this slide, as this and the next slide are probably the most technical. But yeah, so Echoprime consists of video encoder, text encoder, view classifier, and anatomical attention module. First, encoders are contrastively trained to learn to map the video report pairs. So once they're trained, the video encoder would take a video as input and map it to its corresponding text report. And the text encoder, so video encoder would take the video as input and map it to the corresponding vector representation in the latent space. And then the text encoder would take the report as input and map it to the vector representation too. And then videos and reports from the same study are going to be close to each other in the latent space. So if you can see in the multimodal embedding plot at the top, if we focus on the red cluster of points, the cross represent a single report and dot represent or like a circle represent a single video. And all the videos and the reports that belong to the same study are going to be grouped together in the latent space. Next, we train a view classifier. We train a view classifier separately to predict the view from this echo video into one of the 58 most common echocardiography views. And here you can see the view classification UMAP plot of we took the activations from the second to the last layer and did a UMAP of those activations just to visualize that it's actually pretty separable in the latent space, and the view classifier works pretty well. Because these views are usually defined by the echo guidelines, so they are actually very visually distinct, and the model was able to pick up that with well, like a label dataset. But then how do we inject this view information into the Echoprime model? We came up with anatomical attention module using multiple instance learning. So the goal was here, given that we have embeddings for each video, how can we weight these embeddings based on what anatomical section is being analyzed? So essentially, we wanted to learn how to weight different views based on the section that's being analyzed. And using multiple instance learning, we were able to derive this matrix that you see to the right. And to interpret this matrix better, you can say that, say, when you analyze left ventricle is not maybe visible in all of the views. It's only visible in certain views. So we are going to weight the embeddings of these views more rather than the views where their left ventricle is not visible, right? So just like some views are more informative than others for certain sections, and let's include that in the model. Using the view classifier and the anatomical attention module, we were able to inject this information into previously trained contrastive model. And then during the inference, we take, so you can see in the figure C, subfigure C, during the inference, we take all the videos obtained during a single echocardiography study. We first assign the view to each of them using a view classifier, and then we map them to their corresponding vector representation using a contrastive encoder. And finally, we retrieve the report section by section, weighted by, or informed and weighted by anatomical attention module. All right, so this is the overview of the design. I included one more slide to talk about some details, some training details. And if there are more questions about in-depth training details, I'm happy to answer them. Yeah, so since this is a little bit more technical group, I included a few more additional information that were important design choices in our training process compared to previously published approaches. So first, we feed in videos instead of just images. So our input data is 16 times 224 times 224 video. So 16 frames and height and width are 224 and 224. We cut out 16 frames with a stride of 2 from the full echo video. And then for the video encoder, okay, so just backtracking, I think the video data is important specifically for echocardiography because many of the defects are visible, or many of the diseases and features are visible from the temporal information. So just using the images, you might not be able to predict valves opening and closing correctly, or ejection fraction, wall motion. I think specifically echocardiography and heart is the structure that needs this temporal information to be analyzed correctly. And then that's why for the video encoder, we picked the multi-vision transformer. This is a transformer-based architecture, but it's proven to work well for videos such that it understands the temporal sequence. So previous transformers, if you shuffle the frames in the video, they're going to give the same output, whereas for the MVIT, it knows actually the order of the frames and it's temporally consistent. For our latent space, the dimension of the multimodal embedding latent space is 512. And then we picked the Biomed BERT model as a text encoder. So a BERT is a sequence-to-sequence model, but it can be adapted to act as an encoder by taking the CLS token and then projecting it to 512 dimensions. We took the pre-trained weights for Biomed BERT from Biomed BERT is actually just BERT pre-trained on PubMed abstract, so it already had some biomedical context, and we believe that this sped up learning because it didn't need to relearn the medical literature. And this Biomed BERT allows us to read up to 512 tokens, which is a long context window, and that means that all the report text was able to be projected to vectors. As for the view classifier, as I mentioned previously, we trained the view classifier separately, and we use the context-based architecture, image-based architecture for the view classifier. Based on our experiments, we found that it's enough to have the image-based architecture to recognize the view rather than the video, because sonographers are often able to tell the view just from a single frame rather than the whole video. And this worked pretty well, classified into 58 common echocardiography views. Then for the multiple instance learning, we use the approach also mentioned in the, or like explained in the multiple instance attention paper. On the bottom right, you can see the exact architecture, but essentially we trained 2 fully connected networks and then stripped out this MIL component. We needed to be able to take variable instances input. So because sometimes the number of videos per study can vary, we needed to learn how to weight them by the view. So right, we trained this kind of simple linear architecture in the bottom right, where video encoder and view classifier are frozen, and then we strip out this MIL attention that essentially transforms into a function that, given the view and the section that you're currently analyzing, it gives you the weight of how important this view is. And finally, as for the compute, we trained this model on 2 NVIDIA RTX A6000 GPUs with a batch size of 32. The training took approximately 1 month. All right, so now I'm moving on to the results. We first confirmed our hypothesis that giving the model the access to the full study improves the performance. So namely, we selected these 2 metrics, aortic regurgitation and LV ejection fraction, and then we inspected the accuracy as we included more data. we can see that the accuracy progressively improves from prediction on a single image to a single video, and then to multiple videos in a full study, and finally to applying the Echoprime weighting. With Echoprime weighting, we got the best performance. These two specific metrics show us more like the benefit of including the motion in the model, because temporal information is not available in just a single image. But yeah, you can see that it progressively improves as we give the model more data and as the model is able to synthesize the more data. We think that previously the main limitation, so the main reason the models didn't include all the information was just because the architectures, there were no suitable architectures for such cases. All right, so then we also evaluated Echoprime on 20 different tasks and compared it to the prior models of the same type. So Echoprime is what it's called a foundation model, meaning that it can perform a wide variety of tasks with just a single set of weights. And the Echoprime is the first foundation model specifically trained for that can comprehensively analyze echocardiograms and use also like the synthesize information across the whole study. We compared it to the previously developed models BioMedClip and EchoClip. BioMedClip is a foundation model for generally biological imaging or biomedical imaging, and then EchoClip is a model previously published by our group, also a foundation model, but limited in this case to single images or single frames. And then you can see in the spider web plot that Echoprime outperformed on all the tasks, previous models on all the tasks, and often by a significant margin. I think the notable difference is on tasks that require temporal information. And this spider web plot is on the external dataset. This is showing the results on the Stanford Healthcare dataset, and you can find the spider web plot for the internal dataset in the paper and some more in detail results. And as a takeaway, why do we think our model outperforms the previous two? First, as our main kind of hypothesis, that we actually are able to synthesize all the information from the study. And then second, compared to BioMedClip, Echoprime is actually fine-tuned on specifically echocardiography. But then also we compared Echoprime with previous task-specific models. Task-specific is different from the foundation model, meaning that it's a single model developed to predict a single task. And often the public opinion is that task-specific models are more accurate than the models that are able to, the public opinion is there's a trade-off between the how general the model is and how accurate it is. But in this case, we found that Echoprime also outperformed the existing task-specific models. So reviewing the literature, we were able to find 6 task-specific models, and in all of them, Echoprime either outperformed them or matched the performance. But not only that, because Echoprime generates the full report, it can handle more than 100 tasks for which no previous models were developed. So you can imagine that a significant effort comes behind developing such a task-specific and then writing a paper about it, validating it. But then Echoprime can just handle 100 immediately without having 100 separate weights, 100 separate models, right? And then additionally, we also try to see if Echoprime can predict the rare diseases that are not commonly present in the sonographer initial report, such as ST myocardial infarction and amyloidosis. We did that by finding, say, 50 positive cases or a small set of positive cases, which is, and then fine-tuning fully connected network on top of Echoprime. This is known as a few-shot learning. And in the setting of few-shot learning, Echoprime was We did both KNN probing and linear probing, where KNN is like K nearest neighbor on top of Echoprime embeddings, and linear probing is just a fully connected network on top of Echoprime embedding. And then we showed that Echoprime can get great performance on both STEMI and amyloidosis tasks with AURC up to 0.92 for STEMI and 0.96 for amyloidosis. And I think these experiments showed us that our model understands echocardiography as a whole, and it's able to adjust its adjust its weights and recognize new tasks with just a few positive cases. Then talking about the interpretability, which is often a problem in AI models in medical sphere. We have this anatomical attention module where we weight different views based on what section is currently being generated. And then using multiple instance learning, we get the importance matrix. To the right, you can see the focus of our Echoprime model. And to the left, we ask 3 different cardiologists to annotate the importance of views based on the section being analyzed manually. And as you can see, there's strong resemblance of these two importance matrices. So for example, we can see that for the left ventricle, apical views are the most important, whereas for aorta, in both matrices, SSN view was highlighted. Right, so we can see here that Echoprime rediscovered what views are important when analyzing different parts of echocardiograms. And to conclude the presentation, I'm going to talk about our future directions and some of the concluding thoughts. So first, we conducted internal A/B testing by asking a few clinical experts to annotate to recognize what is the sonographer written report and what is AI generated report. And clinical experts in our team were often unable to tell the difference between AI generated and human written report for the same study. And given those results, our next step is concluding a rigorous randomized controlled trial where where 50% of the sonographer written reports will be replaced with AI generated reports, and then we will analyze which subgroup undergoes more edits or changes by a cardiologist. We are optimistic about Echoprime, and we think that Echoprime can significantly reduce the time physicians spend on writing these reports. And we also think that Echoprime can minimize physician-to-physician variability when analyzing echocardiography studies. As for the future research direction, Echoprime is the first model that can synthesize the information across all ultrasound scans, but we think there is opportunity in including and synthesizing information from more modalities and medical records, such as ECGs, MRIs, CT scans, and also medical tabular data. As we discussed previously, I think the main bottleneck to including more data was the architecture of the model. And we think that as the machine learning field is improving and the architectures, medical machine learning will too. And ideally, we would have AI model that can take in all this information and that are available to the physician when making the report or diagnosis, and then be as informed as the physician is. So sometimes it's not reasonable to expect from the model to make a correct diagnosis given only limited information. And yeah, given that, I think these are some of our thoughts for the future research, and we are happy to see how others approach this problem of diagnosing and interpreting cardiac health. We publicly released the code, weights, and the demo for Echoprime, so you can either play with it and reproduce our results, or use it to get interpretations for your echocardiogram, or fine-tune your models for echocardiography. And we hope that this will be a useful resource to medical and AI communities. All right, so I'm going to stop the presentation here, and I'm going to move to the demo. The idea behind the demo is that as soon as the study comes onto the packed system, the inference script runs. And once the inference script runs, the inference script, what it does is essentially processes the image data from the DICOMs, which is the format that images are usually saved in, and then runs the inference, runs the Echoprime inference and generates the report. I'm going to show my screen, or I'm going to show you the view that a physician would see once the Echoprime runs. Give me a second.
Milos, this is like super exciting. And thank you for doing the demo too, because it makes it real for so many people to see how it works. So thank you for doing the demo too.
Yeah, for sure. So let me see. Okay, so right. I mean, now this single study is processed, and you can see my screen, right? Yeah. So on the left, you can see all the videos that are
I think we are just
belong to.
seeing a black screen with like a darker black in the middle.
Okay, thank you for telling me. All right, I'm
Sure, no worries.
resharing and then reloading
That's
this.
perfect.
And so on the left, you can see all the videos that are uploaded from a single study. The view is assigned to each of them. So you can see in the top left is the view written in blue. And then Echoprime focuses on certain views based on the section that's being analyzed. And views highlighted in blue are the ones that Echoprime is currently focusing on. And the same thumbnails that are highlighted are also shown as videos in the middle screen. And right, for now, we are just highlighting the 9 most important views. And you can see in the right section, on the right side, Echoprime is showing the interpretations, and it's retrieving them section by section. So, for example, now the yellow highlighted section is being generated, and different views are being analyzed for each section. So just highlighting how we need to weight the different views for each section, we need to prioritize different views. Yeah, so these are the full interpretations. Once the algorithm finishes, it's going to give a full report. So you can see that it's a full-length report analyzing everything section by section. Idea is that the cardiologist will receive both the videos from the study and then this preliminary report, which they can then analyze and perhaps fix or modify downstream. And our future RCT is supposed to confirm how often do cardiologists need to modify this report and how accurate it is. And I think with this, I'm going to finish the presentation and the demo, and we can maybe move on to some thoughts that Emin has about the implication of this model in clinical practice and generally foundation models for medical sphere.
All right, that's great. I think I'm gonna keep the questions for the end. So I'm gonna have it followed by Dr. Chiu
Yeah.
to have his presentation, and we'll take the questions at the end.
Do you want me to keep the demo just like this, or do you have a few slides, Emin?
I have one slide to share with the concluding remarks. Yeah, thank you, Milos and Piyush for the invitation. And it's a very great presentation and shows us the potential for this kind of vision language model. So here are some of my thoughts about the potential of using these kind of models. So as a clinicians, I think the potential for vision language model, especially in echo, is huge, right? So it's actually the model actually demonstrate the ability to fully generate an automatic diagnosis based on only like raw videos. And I think it's highlights some of the potential paradigm shift in healthcare, especially in echo diagnosis. And and in echo diagnosis, like most of the echo, diagnosis were more like based on guideline and also based on reimbursement. So the importance of how these kind of visual language model relied on a lot of the raw data might affect how doctors or affect technicians perform echocardiograms, improve them, encourage the hospital or encourage the doctors to do more raw data and to improve diagnostic consistency and to reduce like operator variabilities. But these kind of the visual language model also shows some of the data insufficient bottleneck. So in these years working in David's lab and also working with Milos, we also noticed that the scaling though are still exist. So to remind that the Echoprime was trained on 112 million raw video data to get this like such a great performance on the visual language model. And for one of my recent studies, it's about training a supervised learning task for using the raw echo to detect pericardial effusion, to grade it, and also to classify a cardiac tamponade from the raw video. And even these kind of image-based, video-based supervised learning tasks will still require 1.5 million raw video data to ensure that the model was performed robust and consistent. So getting a large number of data set are still a really big bottleneck for a lot of hospitals in the world, especially including my hospital in Taiwan. So it's hard to first have access to this large of the data set, and it takes years of effort to know and to learn how to process this data set to be a useful information and to leverage the data set to be trained for these kind of large language model. And also these kind of data set infrastructure require collaboration between both clinicians and engineers. So I would like to emphasize the importance of the collaboration and the close work between clinician and engineer on both sides. Like in the recent chat with David, where metaphors in like working in these kind of AI is like riding a bicycle. Clinicians and engineers are like the two wheels of the bicycle. You can like lose either of the wheels to make any of the AI healthcare project work. And the clinicians developing these AI project, we focus more on clinical implications and how to evaluate the model efficiently, both retrospectively and also prospectively. And we have more insights on how data should be collected and how data should be collected and processed to reduce bias or overfitting in the future. And engineer can focus more on how to efficiently gathering the data, how to leverage the most up-to-date algorithms, and also innovative tools on developing these kind of AI algorithms. So working collaboration closely between clinicians and engineers are definitely a very important part of developing such fascinating project like the Echoprime. And however, even though we see a lot of the improvement based on large language model and vision language model in the recent 2 to 3 years, in the clinical healthcare AI, we should still focus more on the clinical utility part of the AI healthcare project and how they can affect or benefit clinical practice. And in fact, we can see that most of these projects are more like efficiency, based project, or like releasing the labor from clinicians. But as a clinicians, we would like to see more of how these kind of research can really improve the patient's solid outcome, like mortality and mobilities. So there are, like, back to 1980s and 1990s, there are some kind of computer-aided diagnostic based on computer vision tools rather than machine learning. So one previous study published in NEJM shows that there are tools use mammography image to diagnose, to get early detection for breast cancer. And these kind of tools have very high sensitivity and specificity. And the study shows that once the tool, FDA-approved tools was launched, we have more early detection for breast cancer in the general population. But on the other hand, it also creates a very high false positive biopsy rate. So it means more patients just receive biopsy, but without breast cancer. And these kind of study also shows that the general improvement patient solid outcome like mortality in breast cancer did not improved. And there is also very one recent studies about using AI ECG to diagnose cardiomyopathy, which is a very dangerous structural heart disease for patients during their pregnancies. And while the AI ECG models successfully have higher detection rate for the cardiomyopathy for pregnancy women, unfortunately, in the AI intervention arm, there exists to be a higher mortality rate for these patients. So these kind of studies shows the importance of the AI models the clinical utility, and how should we design a clinical study, a prospective study to really validate these kind of AI model and to see what the potential of this fascinating large vision language model can work for us. And that's my concluding thought. Thank you again for Milos for this wonderful works and the fascinating presentation. I'll give the time back to the host.
Yeah, thank you so much. Those are some great thoughts, and I think especially the emphasis on collaboration and validation is very much appreciated. I do want to take this question from Venkat here in the chat about do you have any suggestions for lay clinicians like me as far as ways to get involved in developing algorithms like Echoprime in collaboration with engineers who are savvy with this. So my 2 cents before I ask Milos and Dr. Chiu to talk about it is, first of all, don't try this at home. It is something that requires, in my personal experience, and of course, we'll have the speakers talk about it, a lot of experience, a lot of resources. And that's why my former question too, which was very well addressed, like what kind of compute resources do you need for this? So it is not something that you can just do at home. Probably you require some organizational structure behind you to do it, but I'll let the speakers address that question.
Right. As the structure goes, I think in our lab, we worked very hard over the last couple of years to build both the storage and the GPU compute to make such models. So I think it's a challenge to store 12 million echocardiograms locally. So we have a good engineer Kai Christensen, who built the NAS storage, and then this is terabytes and terabytes of data, and then you have to consider that this all have to be loaded very fast into machine learning models. So it needs to be fast read, fast write memory. And then as for the GPU compute, many companies now sell GPU ready devices, so it's a little bit easier to access these days. But it is challenging task, but not impossible to achieve with enough effort and motivation. And as for how you can get involved as the clinician, I think Emin might have some more insights because he's both MD and then PhD in computer science.
Yeah, I would like to echo Milos. It's definitely take a lot of works, especially building the infrastructure, both on the data set side and also the computing resource, the storage resources, in order to achieve this kind of research. And I saw some participants asking questions about how clinicians can be involved in these kind of pioneering project. I think with all the help of language model, we have all the kind of resources, not just Google now. We have ChatGPT, we have Claude, we have Gemini, and it's the barrier for learning new knowledge are definitely easier compared to like 5 years ago. And like from learning coding, like 5 years ago when I first started learning coding, I have to, go through all the scikit-learn PyTorch documents and also go through some of the debug, website like Stack Overflow to learn all the knowledge and debugging all the code, from the beginning. And now the ChatGPT and Gemini can replace us to do a lot of easy work for us. So it's actually the barrier for learning new things are so much easier, and we get so much resources. So the simplest way we just get started, do it, and connect with others, like using the BrainX platform, and you will know like more of the engineer on the other side are doing the same things.
Yeah, that's great. And Venkat, I did put in a recently published paper from our team about how to get started for clinicians, whether your goal is to just learn the basics of AI versus, doing some hands-on project versus, doing some innovation work, commercial level development, how to approach it. So hopefully you find that publication helpful and interesting. But I think the collaboration is key, and that's what we emphasize at our research lab too. We have clinicians and we have the engineers or the data scientists of all different backgrounds and levels. And it's not just the development part. I would also say the validation part is extremely important. That's where we need a lot of clinicians too. That's what a lot of engineers and data scientists seek too. So it's not just the development of the model, but you can probably get engaged in the validation part of it, in the clinical space. How do we validate? That's the need of the hour before these models get to the clinical implementation side, or even after the clinical implementation side. And there are a lot of organizations that are seeking clinician partners. I would encourage you to follow BrainX on LinkedIn. We post a lot of this information when people are looking for these roles and jobs. So follow that, and you'll find that that is another space. So you don't have to get involved necessarily in just the technical coding part of it. But you can also, just like any other drug or device validation, get involved in the validation part of it. I encourage you to think about this. I do see Nibras over here. He's a very prominent clinician, ICU physician, researcher, and I want to ask him what he thinks of this, especially because he has led some amazing work in echocardiography, doing point of care ultrasound, we call POCUS, and echocardiography, developed some amazing tools. And we have been talking about like how to automate some of those and his expertise with AI. And I thought like I'll have him here so that he is somebody who has a lot of experience in this and a vision for the future. But the question I specifically was trying to relate to this was like, cardiologists will many times say, I don't need this. I am good at this. It takes me 5 minutes to look through this and I can do it. Whereas when you think about other clinicians, and that's where I was going with the democratizing AI part of it, are probably the ones who need it more. So the ones who need it for educational purpose, I think it would be a great tool for educating residents, fellows, other groups of trainees. It would be great for places where you don't have cardiologists readily available. So distant places, at least you get some screening right away, and you can then use your judgment and get an idea. So, Nibras, what do you think? How do you see the value of this?
Absolutely. Thank you, Piyush, for inviting me to this amazing presentation, and thank you for creating this BrainX community to collaborate, to help collaborating between physician and scientists. And Milos and Ayman, the presentation is outstanding. I see that the models utilizing multiple views is complicated, requires a lot of views, require a lot of CPU, GPU, and they utilize images obtained by cardiologists or echo technicians. Is there any work done on images obtained by like point of care ultrasound clinicians users? So it's the images that are obtained after limited training. They're not perfect. So one of the problems I see with this is having database create enough images or database of these such images that are not curated to perfection. So working on these images to improve efficiency for cardiologists is excellent, but where I see this going to be very, very helpful is, as you all said, democratizing point-of-care ultrasound. And the way I can see this is using it in less perfect images, maybe more accessible windows. So instead of feeding the AI multiple windows, have you ever experienced using the AI applying only a single window that's accessible, done by point-of-care sonographers? And the other thing is, it would be more useful if you identify the clinical context. For instance, do interpretation based on clinical context, applying AI for patients who are already hypotensives, because I can see the use for this modality mainly is going to be on the diseases that are very that you don't have a lot of time to do the diagnosis in order to start management, like in cardiac arrest or sepsis, and make it available for the frontline providers.
Yeah, thank you for all the feedback and questions. I think the main use that we're currently aiming for is that, at least in the hospital systems that we're affiliated with, the standard echocardiography workflow is that sonographers write a preliminary report. I know that some, at least I learned that in some of the healthcare centers, sonographers don't write a report, but just give the measurements on the image. But at least in our healthcare system, yeah, sonographers write the preliminary report, which then goes to cardiologists, and then they make final changes. So then we think that just replacing these preliminary reports written by sonographers, instead to be written by AI, can be the use case of Echoprime.
I mean, any thoughts from you?
Yeah, thank you, Nebras, for this is a very good feedback and questions. So when we think about echo, of course, there are not just like standardized echo, like big machine echo. We have point of care ultrasound. Like as an ER physician, I definitely use more point of care handheld ultrasound, like Lumify, Butterfly, those kind of things. And typically the echo workflow can be divided into like capturing the picture, the image and making a diagnosis, and before is like image or video acquisition, right? So what Echoprime has focused on is, I would say, in a different setting for point of care ultrasound. It's more like in a hospital system where patients receiving a full standardized echocardiograms, where most likely a technician records like dozens of videos and images to get the fully final report. And me personally, I do agree with Nebras about the importance of image acquisition. Some of my previous studies are focusing on what the peers already talked about, using AI to educate novice users how to get like the best quality of the image or videos. So some of my recent studies is about using AI to guide unexperienced users to perform FAST, which is the point of care ultrasound for trauma patients, and also for AAA, aortic artery aneurysm diagnosis, and also focus on image acquisition. So I think both of these kind of direction of the studies are definitely required to fully, expose the potential for AI. So yeah, that's my feedbacks.
I think what I sense is all the excitement. Nebras wants to go to the next level, but I think we have to get to Echoprime to get to the next level, to add to other contexts. And I think Milos had already stated that they're looking to integrate other data to build in that context to get you what you need, Nebras. But it's our excitement. We want to get to the next level. I know we are about time, but just wanted to get like a couple of technical questions answered. One thing I feel is
can I have one question?
Yeah,
though?
absolutely.
So I see that you did your training on 12 million videos. I do have data for a few thousands of pathology images on a single view. What is the weight of few thousands of images? comparing to millions? Would that be impactful?
I think it depends on the task that you're trying to learn. Say view classification, given that it's easy, assuming that it's easy, maybe a few thousand can be done, but essentially, I don't think any of the models that we trained in the lab are trained on like fewer than like 50 or 100K images. But it's also that it would be interesting to do the studies, what happens with these echo-specific models once you scale up the data. We do have a plot that I can share maybe after the presentation, but definitely data scale improves the accuracy by a lot. So you might be able to get a few like models, but just training on 1,000 examples might not be optimal. But now that there is like Echoprime, you would be able to, because if you start training from Echoprime and just fine tune on your 1,000 or 2,000 images, we think that this would be basically a state-of-art accuracy. So if you start your model with just Echoprime weights and do this transfer learning, like in the case of amyloidosis and STEMI that we did, my experience is that you would be able to get the optimal accuracy as if you trained on full data, so on like 12 million plus thousand data sets.
Yeah, so essentially, you already have the foundation model built, so you could fine tune using his data for a particular task and see. So Nibras, that's how I would approach it instead of trying to build it from scratch. But also related to that was you had mentioned that for those issues, the amyloidosis and all, you did like the few shot learning for those, or was it fine tuning? Slightly
There's
technical and
linear
different.
probing. So linear probing is the approach where everything is frozen, but I just fine-tuned one single layer on top of it. Linear and K&N probing.
Okay.
So just like a few parameters, the training takes a minute, 2 minutes, right? But it was 50, about, I think, 50 for amyloidosis positive cases, and for STEMI, maybe 100 positive cases. I saw your question, but this is like the order of data.
Got it. Got it. And I actually had one other question. If you can go back to that spider web that you had, I did see variation in the performance based on the structure that it was trying to interpret. And I wanted your thoughts on that, especially when we look at ejection fraction, LVEF. With that level of data, I would have thought that the LVEF estimation would have been better compared to, say, the RV systolic function, or if you look at the left atrium dilation, that's lower performance compared to, say, your mitral annular classification. What do you think explains the variation in performance over here? Sorry, you're on mute.
Yeah, so thank you. I think for ejection fraction, it's calculated in R2. All the others are binary metrics, so it's AURC. So maybe this plot is not extremely informative, but or it is informative, but it's not maybe representative. Like ejection fraction is not performing worse than others. It's actually outperforms like state-of-the-art task-specific model. So I think it's very good. It's on the order of 0.81 R2 and mean absolute error from 4 to 5 MAE. But yeah, just how the plot is displayed. And then for some of the other metrics, there is also the thing that we are getting this from the reports written by physicians. So sometimes we do the template matching to get the ground truth labels. So it's also like how well is the report written. So there's right, we assume that everything that was present was really written in the ground truth report. But yeah, I mean, I think that explains part of the variation in these metrics. Say that if there are 10 different ways to say left atrium dilation is present, or if you say LA dilation is present, or so, this is like a hard thing to catch all the phrases in the ground truth. And as for the model, I think the only other way to see how good human to human variation is, and then compare it where set that as a baseline, right? And this is, I think, what we plan to do in the next. In other words, to simplify it, for all of these, there is probably like different baseline for all of these metrics shown in the spiderweb plot.
I see.
And then I think that the only way to learn what this baseline is, at least for physician to physician, then we would have to do the RCT.
Perfect. Okay, last related question. So when you have the report generation over there, is there a way to show the confidence interval in there to gain trust amongst the physicians so as to show that maybe the LVF estimation, you use caution when you're interpreting this compared to, say, something else which it's predicting is with a higher degree of confidence? Is there a way to demonstrate that in there? Any thoughts on that?
Yeah. So you're asking that once we provide like metrics, interpretations, how confident is the model that these are correct
Yeah.
metrics? There is a way, if you are interested only in the metrics rather than the report. So if we have the end-to-end report just generated, then it's hard to just do it section by section, or like it's hard to do it measurement by measurement and say how confident it is. But if you wanted to do it just measurement to measurement rather than predicting the report, so for example, if your input is rather than generating the report, it's just LVF is 60, LA dilation present, etc., then you could fine tune, say, a linear probing head where you do categorical classification and then use in the standard way the confidence intervals, like right, like you just get like a logit from 0 to 1 and then you can say this is like the confident. But for the report generation, for now it's end to end. But if there is I'm saying that there is a way to implement it with the confidence intervals, if that's what you're interested in.
All right, guys, I think we are beyond time, but we could do this all day. We're so excited about this. So congratulations on your awesome work. I'm sure this will lead to a bigger and brighter future. And I'm going to end this event by thanking the speakers, thanking all the participants over here thank you for joining us. Great discussion, great work. We'll post this on our YouTube channel, a whole host of resources that are available through BrainX community that are available on the screen. So please join us and follow us over there and contribute to the future development of AI in healthcare. And this is an amazing year-ending session. So thank you, everyone. Until next time in 2025. Take care.